Now, the next topic we'll look at in the context of the randomized complete block design is relative efficiency. When a randomized complete block design has been used in an experimental situation, and once the resulting data have been analyzed, an important question to consider is whether blocking has been effective, and if so, to what extent the design has provided more information than would have been provided had blocking not been used and a completely randomized design used for the experiment instead. This is not an easy question to answer because a completely randomized design was not used, and so we don't have data from that type of experiment. This question is addressed, however, by the relative efficiency, which compares the observed efficiency of the randomized complete block design to an estimate of what the efficiency of a completely randomized design would have been had it actually been used. Now, interestingly, it computes this estimate of what the efficiency would have been for a completely randomized design using data from the randomized complete block experiment itself. Now, the formula for the relative efficiency is given by this expression. So the relative efficiency is R minus 1, R being the number of blocks used, times MSR plus R times T minus 1, again T being the number of treatments used, all over T times R, which is the total number of observations minus 1, times MSE. Now MSR and MSE are the mean square due to blocks and the mean square error, respectively, from the ANOVA table for the completely randomized, the randomized complete block design. Okay, so once we've done that analysis, that ANOVA for the randomized complete block design, we can use the mean square for blocks and the mean square error to compute this measure of relative efficiency. Now, how do we interpret the relative efficiency? The relative efficiency gives how many times larger the number of replications would have to have been using a completely randomized design in order for that design to provide the same level of efficiency as that provided by the randomized complete block design that was actually used. If the relative efficiency is equal to 1 or close to 1, then that it would indicate that blocking has not been that effective and perhaps a completely randomized design could have been used. To the extent that the relative efficiency is greater than 1, though, blocking has been effective. And so the larger the relative efficiency, the greater it is than 1, then we can conclude that the more effective blocking has been. Now, the particular interpretation is as follows, and we will we'll denote the relative efficiency as being equal to K. All right, and so we're going to consider the situation where K is greater than 1. So in that situation, what that tells us, what a value of K, the relative efficiency greater than 1 tells us, is that a completely randomized design would have required K times the sample size that was actually used in the randomized complete block design to have the same level of efficiency as that RCB. Let me say that again. If K is the relative, if the relative efficiency is equal to K, then a completely randomized design would have required K times the sample size that was actually used in the randomized complete block design to have that same level of efficiency. So let's look at this in the context of an example. This will be example 3.2, and we're going to refer back to the results from example 3.1, where we were comparing 5 treatments in the context of a randomized complete block design. And so the question would be, what is the relative efficiency of that design compared to a completely randomized design? And so we want to calculate and interpret the relative efficiency. So using the values from the ANOVA table that we constructed in example 3.1, the relative efficiency is given by this formula here. So the relative efficiency, 3 times MSR, plus R times T minus 1, so 4 times the CT was 5, so 1 less than that is 4, times the MSE, and then times the total number of degrees of freedom, which is 19, T times R minus 1, times MSE from metanola. And so when we calculate this, we get a value that's approximately 23.5. Now, what this tells us is that if we had used a completely randomized design instead, then that completely randomized design would have required 23.5 times more observations than the randomized complete block design used in order to attain the same level of efficiency that was attained by that randomized complete block design. Now, since there were 20 observations used in the randomized complete block design, and remember that result was highly significant. So since 4 observations were used in that randomized complete block design, 4 replications per treatment, you'll recall, then a completely randomized design would have required 470 observations. In other words, 94 replications per treatment in order to attain the same level of efficiency as that which was obtained by the randomized complete block design. And so this shows us that blocking for this particular experiment, blocking has been highly effective, highly effective. All right, so that is relative efficiency. When we are talking about relative efficiency in the context of a randomized complete block design, we are always comparing to the situation where blocking was not used, and that would be a completely randomized design.